So hello everyone. Today we'll be reviewing the key concepts that we have covered in our regular classes in the last 3 weeks. That is week 4 to week 6. So this kind of review is important because here we'll be summarizing the key concepts that we have received in those classes. So I will not going for detailed derivation. I will just only pinpoint the key features, the key concepts that we have covered in those classes. So what are the key concepts that I have covered in this last 3 weeks? So we can summarize them in the table as we have given there. That is ionization potential of elements, Townsend mechanism for ionization by electron collision, then Townsend's first ionization coefficient, ionization by positive ion collision, photons, cathode processes, penning effect, effect of contaminants, and then AC and DC breakdown concepts, Paschen's law. So, in this last 3 weeks, we have covered many of the very important aspects of plasma discharge, which we must know to understand how a plasma device operates. Then, to understand the process chemistry, various key aspects that we have covered includes partition function hierarchy, thermodynamic and transport properties, elementary ideas on variation of these properties for common plasma gases as a function of pressure and temperature. Then the concept of thermal and chemical non-equilibrium. So as far as process is concerned, you must know the thermodynamic and transport properties because they are the key parameters which control the behavior of plasma. So what will be the enthalpy content, what will be the thermal conductivity, what will be the electrical conductivity, all these things decides the property of the plasma, and that you can understand when you know these key concepts. Now then comes the plasma devices. So in that we have covered several of the very important devices. These thermal plasma devices includes thermionic and thermochemical cathodes, electrode features, discharge characteristics, transformation from glow to wax, arc characteristics, arc devices, design features, then cathode and anode heat transfer in designing a torch, required power supply features as well. So these are the concepts, they are very much required to when you are going to design a plasma device for certain applications. So these concepts we have covered in the last 3 weeks. So in a nutshell, actually we have covered many of the very important aspects for plasma generation, plasma understanding, and plasma device fabrication. So starting with the ionization potential, this is a very important graph because whenever you want to generate a plasma, the first thing need to know is that what is the ionization potential of the plasma gas that you are going to consider. It may be say nitrogen, oxygen like molecular gases, or it may be inert gases like argon, neon like that, or it may be metallic gases. So we need to know the ionization potentials of them. So the inert gases, as we have discussed many times in the class, this is a very important feature, I am repeating it here, that they are having the highest ionization potential because of their field cell configuration. So they are coming at the peaks in this, in this graph, ionization potentials as a function of Z. So they are appearing at helium, neon, argon, krypton, xenon, radon, like that. And then as you increase the electron from the inert cell configuration, their ionization potential drops. Then as they become closer to next inert gas configuration, then the ionization starts gradually increasing and then reaches the peak at the inert cell configuration, inert gas configuration, then just drops down. So this is the kind of thing. And when I am talking about these molecular gases, so they need first dissociation, and after that they go for ionization. So dissociation is another thing which we need to consider, this dissociation energy of the molecules. So once they get dissociated, they become atomized, then this graph applies there. Then the other thing, many of the times we encounter the metallic contaminants in the plasma. So this metallic contaminants may be in the this transition metal region. So there you see that they are having pretty low ionization energy. So once these metallic contaminants enter into the plasma, they can get very easily ionized, and then they can contribute to the ions and electrons in a manner that they influence the whole plasma discharge. Now, when we are going to create the plasma, then the primary method is the Townsend discharge. So what is done there? Some electron emitting electrodes are used, and they are either thermionic electrodes or they may be some field emitting electrodes. So they are basically generating some electrons under certain conditions, and then those electrons are getting accelerated in an electric field. And when they are getting accelerated, they are colliding the different neutral particles on their way, and thereby they are transferring their energy to the atoms. And if the supplied energy is more than the ionization energy of that atom, then they get ionized. But the primary problem was that when you are going to accelerate, it is not getting enough space for acceleration. Before they get some significant amount of energy, they get collided with another atom, then they are no more accelerated. So they come to standstill conditions, again they start getting acceleration. So this problem that they are not getting enough physical space to get accelerated, this is arising because we are now keeping the gas at certain pressure. So higher the pressure, lower is the mean free path. So the free path between two collisions, that should increase so that they get sufficient amount of energy for ionizing the atoms. So now in this Townsend ionization mechanism, they play a very important role, and the whole breakdown mechanism can be formulated in terms of this Townsend ionization process. So here we define two ionization coefficients. One is Townsend's first ionization coefficient and Townsend's second ionization coefficient, that is also there, but there is mainly the first ionization coefficient, which is defined like that: number of electrons produced per unit length in the direction of the applied field in the process out of a single electron. So number of electrons produced per unit length in the direction of the applied field out of a single electron, that we call the Townsend's first ionization coefficient. So with this definition, what we obtained? We obtained that expression for alpha goes like 1 by lambda 0 exponential minus lambda I by lambda 0. So, this lambda I is the free path that is required to gain the ionization potential Vi under a given electric field E. So, lambda I is equal to Vi by E as we have given over here. Now, you know that when we express these things in terms of pressure and electric field, then the expression for alpha we got is equal to A multiplied by pressure exponential of minus Bp by E, where A and B are some constants, P is the pressure and E is the electric field. So, we get a very nice expression for alpha in terms of pressure and electric field, both of which are can be estimated experimentally. So, that is the beauty of this equation. Now, when we are having a medium of say length dx, then number of electrons that will be generated per electron will be this is alpha into dx. If n electrons are impinged, then total number of electrons that will be generated out of this thin region of medium is dn equal to alpha n dx. Now, if this now medium is of length say d, then the total number of electrons that will be produced, you can integrate from n0 to nd. So, n0 is the initial number of electrons that get impinged on that medium. Then what you get, nd, that is number of electrons generated at the end of the medium of length d is n0 exponential of alpha d. So nice an expression, nd equal to n0 exponential of alpha d. So, this is the number of electrons that will be produced in a medium of length d under the Townsend mechanism. So, once we got that, then there are other ionization mechanisms as well. So, ionization by positive ion collision, ionization by photons, cathode processes. So, all these things we discussed there, but the primary mechanism still remains the Townsend mechanism. Now, in this actually ionization scenario, there was one very famous thing that is called Penning effect that we discussed, by which we found that below the ionization potential sometimes we get sufficient ionization when we are introducing specific impurity in the medium. So, this was a very surprise for quite some time. Like this example we elaborated that when we are introducing a small percentage of argon in neon, so this percentage, when I am saying it is a small percentage, it is only around 0.1% of the main gas concentration. So, when you do that, then neon is having a ionization potential, neon is having ionization potential of 21.6 electron volt, and it was observed that if it is mixed with 0.1% of argon, then we were getting copious ionization well below the 21.6 electron volt. So, we are getting a ionization, copious ionization when just the electric field, this electric potential was increased around 15.6 electron volts, which is well below 21.6 electron volt, the ionization potential of neon. So, why this was happening? Later it was explained that this neon is having a metastable level of 16.6 electron volt. So, when the potential applied potential increases to 16.6 electron volt, that metastable level get populated quite significantly. Now, it is well below 21.6 electron volt. Then, when these electrons from this metastable level depopulates, then the radiation that is getting emitted, it is well above the ionization potential of argon, so that is just 15.7 electron volt. So, when you are increasing the potential to 16.6 electron volt, the metastable levels are getting populated, and when they are de-exciting, the radiation that is causing ionization of actually argon, not the neon. So, although the main gas is neon, this argon ionization basically giving you the significant ionization which you observe when you are increasing the potential. So, that is the this Penning effect, and this is due to Penning. Michael Penning is a Dutch physicist. Because of him only, he has done lots of work in this area. Because of him, we could understand this ionization process that can happen due to the presence of metastable levels. Then comes the DC breakdown Paschen law, which is one of the very important law as far as plasma generation is concerned. So, here what we did, we included the effect of Townsend mechanism. So, this is N0 exponential alpha d plus the effect of the photoionization. So, total number of electrons that has been generated equal to the Townsend mechanism plus the electrons contributed by the photoionization mechanism. Because when the discharge happens, lots of photons are created. It is obvious because this plasma means it is a highly emitting object, it is a radiant object. So, radiant because it is emitting photon. Many of the photons do have the ability to ionize the gas. So, total number of electrons that will be generated is Townsend mechanism plus the photoionization mechanism. Now, this photoionization will be depending on again not on N0 but the total number of electrons that has been generated. So, this Np will be a function of N, not N0, because the total excitation will depend on the total number of electrons that has been generated, and the photons will be accordingly produced. So, we express this in proper way. So, this became N, the total number of electrons that has been produced multiplied by this factor. Here alpha already the Townsend's first ionization coefficient, and mu is the absorption coefficient of that gas for that photon, and this mu is including the property of the particular gas that you have introduced, and that is there involved in the plasma generation process. So, we have included all these things in the factor gamma. So, gamma is basically including the property of the gas. Now, what we did, we wanted to know mathematically that this total number of electrons that has been generated, if it is going to be a big breakdown, then N should be very large. That is, we want N to be almost infinite. And if we want to do that, then what we required? We wanted that this denominator should approach 0. And here we made one important approximation that if we assume mu equal to 0 in this condition, then it becomes not necessary but a sufficient condition for the breakdown to happen. So, for that sufficient condition, we got this expression for alpha d like this, and finally from that we obtained the expression for this breakdown potential like this, Bpd divided by log of Apd by log into 1 plus 1 by gamma. Of course, here we have used the expression for the Townsend's first ionization coefficient that we derived earlier, and we expressed E in terms of V and D. This is electric field, so it is voltage divided by the distance. So if D is the discharge gap and Vv is the potential that we have applied, then Vb by D is the electric field. So that we have applied here, and we got the expression for breakdown potential as this one. Now the important thing in this was that this Vb is not function of pressure or distance alone. Interesting property of this equation is that Vb is function of the product P into D. You see here that in the numerator also PD is there, and in the denominator here also PD is there. So you can write that Vb is a function of product P into D. Then what we found that the behavior of the breakdown voltage varies with the product PD like this. So this is the breakdown voltage and this is the breakdown field. What we find that there is a minima. The PD minimum is there, for which we get the minimum breakdown voltage, and we are always looking for that we want to make the breakdown happen at the lowest possible applied voltage. So for that we see here that there is a particular PD value. Now you all know how to find that PD value, so we take the help of this differential and we make this to 0, and then we find what is the value of this minimum breakdown potential. Now the question was, why this particular behavior was there? Why the breakdown voltage comes to a minimum for certain PD and on either side it increases. So let us assume that there is a particular gap and we are increasing or decreasing pressure to get this curve. Now if we are decreasing pressure, you see that in this side we are reaching, then what is happening, too few collisions are happening. So you are not being able to generate sufficient number of electrons. So for breakdown you need to increase the breakdown potential. On the other hand, if you are increasing the pressure, then what you are doing, you are decreasing the mean free path. So again they are not being able to gain sufficient energy between two collisions so that it can cause the breakdown. So again the breakdown voltage is increasing. So this was the explanation. Then what we went for different discharge regimes, and we got this famous curve where we are increasing the voltage from a very low value to high value, and the current, associated currents also we have plotted over here. Now in this there are two very important discharge regimes that we have covered. One is called glow discharge and one is called arc discharge. So usually the glow discharge occurs at low pressure. It is not very low, but also there you can get the glow discharge, but it is always usually at lower pressure, the glow discharge that you get. So this kind of discharge are usually characterized with very high voltage and low current. So low current, typical current of the order of milliampere. So you just see this region here, this is the current in ampere. So here you get some milliampere, and the voltage that usually one apply is of the order of kilovolt kind of thing. So here the voltage is very high and current is low, and this is the usually occurs at lower pressure. So this is the glow discharge plasma. Now a vast range of devices operate in the arc plasma mode. So these are the discharge mode which are usually characterized by high current and low voltage. So here you can see that as the current is increasing, the voltage is decreasing. So usually in ohmic region, what you get? V equal to I into R. R is the resistance of the medium and voltage is proportional to the current. So if current increases, voltage also increases. But here what you are seeing that in this arc region, the current is increasing but the voltage is decreasing. So this is a negative VI characteristic. This is a very important feature of this arc discharges. Now we have already told that the effect of pressure. So typically, about 100 torr or so the plasma, you will see that it is operating the glow discharge. But as soon as you increase the pressure, the same discharge can change to the arc discharge mode. So then we came for the AC discharge mechanism, and here we found that the once you switch from this DC to AC, then apparently at lower frequency, whatever charge you are creating in one cycle, that is getting collected completely. So the behavior is not much different from the DC breakdown mechanism, but as you keep on increasing the frequency, then the charge that has been created here during one breakdown, that is not getting completely cleared in the next cycle. So some charge is getting accumulated inside this. So before the charge reaches the other electrode, the field is reversing. Now the charge which is not getting cleared in this zone, this charge when you are making a AC kind of field, then charge is moving, then moving, then moving, then suddenly the field reverses, then the charge starts moving in opposite direction. So a situation may happen that substantial amount of charge is residing within the discharge gap, and those charges, the Coulomb field that they apply, this is not a small one, and you see the number density of the charge particles. So straight away you will be multiplying by 10 to the power 19, sometimes 10 to the power 17, 10 to the power 19, like that. So this is a huge figure by which you will be multiplying the field, because if you apply the superposition principle, then the field will be due to all the charge particles, and that will be really a very, very significant field which will be assisting the breakdown. So sometimes in AC breakdown we will see that discharge is happening at much lower breakdown voltage. So if we plot this breakdown voltage for AC by breakdown for DC, you see that at lower frequency they are same, because all the charges are getting cleared. But as you are increasing, some charges are staying there, and then what they are doing, they are assisting the breakdown mechanism. But as you are increasing the frequency further, then you see that the breakdown voltage is again increasing. Why? Now a time will come, when you are switching the frequencies, then electrons are very highly mobile, they will be first collected, and these ions will be collected later because they are sluggish, but they also will be collected if the frequency is slow. But that when it is happening that frequency is so high that electrons are also not getting collected, those residual ions which are staying inside the discharge, and they are creating the electric field to assist the breakdown. Now they will be neutralized because electrons are also not getting cleared. So the electrons and ions, they are cancelling each other. So the advantage of additional electric field, what the discharge was getting earlier, that will not be available anymore. So a time will come when the frequency is so high that neither the electrons nor the ions are going to the reaching the electrodes. So that time you see that those electrons can be kept outside, and that is called electrode-less discharge. So that we have discussed in our classes. So this is a very important idea, that AC breakdown can reduce the breakdown voltage that is required for DC. Okay. So this is the discharge scenario that we have obtained. We obtained the critical frequency for ion clearance, electron clearance, and mu is the mobility that is playing the role over here. So you will be getting electron mobility, ion mobility, both of them for respective critical frequency for ion clearance and electron clearance. So now we have to go for this plasma composition once the breakdown has happened. So this will just come to our next class. We will take a short break and we will come back after that. Thank you.